we are the Collège Saint-Pierre's tourist team. During the flight, we gathered 628 records for a total flight duration of 25 seconds. Our RF transceiver lost the CAN signal 17 seconds after the launch because the rocket was out of distance. We received 80% of the data stored on board while the RF link was active. During the flight, the rocket reached an apex at 329 meters from the ground, 11 seconds after the launch.
This is a 3D plot of our CAN's trajectory using Google Earth. The yellow trace represents the path of the CAN during the flight phase. The black marker, which is about 1.5 kilometers away from the launch site, represents the last data point that was successfully received by radio. At that moment, the vertical velocity was about 40 meters per second, and the horizontal velocity was about 90 meters per second. We could see that on the live graphs that were broadcasted on our website. A few seconds later, the CAN got ejected, at only 190 meters above the ground, which is much lower than expected. In comparison, we also plotted the trajectory from our school's team from 2 years ago. For the next few seconds, we had a disturbance in the pressure as air rushed into the CAN, and as a result, the altitude was not precise. Finally, in purple, you can see the landing spot.
This is the temperature data collected by the BMP sensor and our 3 thermistors. The response time of a thermistor is much better than the BMP's. The blue curve is our best thermistor. In less than 3 seconds after ejection, its readings reach the actual air temperature and then increase again as the CAN descends. Let's focus on this thermistor. There were some instabilities. The first group is easily explained by the disturbances when the CAN casing opens before ejection. The second is less clear, possibly an inhomogeneity in the atmosphere. The temperature on the ground was 12.4 and went as low as 7.7 at an absolute altitude of 655 meters. This is the temperature in function of the altitude after the CAN is ejected and the readings catch it up with the actual temperature. The relation is almost linear as expected.
So here is the raw pressure data as a function of time as collected every 70 milliseconds by our BMP 388. The pressure first drops as the rocket gains altitude and then lifts up again as it should. At around 38 seconds, there is a disturbance in the pressure records. We assume that these values might be caused by a turbulent airflow when opening the CANSAT casing at ejection time. It makes those values irrelevant for altitude calculation. At touchdown, there is a discontinuity in the pressure measurements. Our hypothesis is that given our excessive descent velocity, 20 meters per second, there was a significant dynamic pressure which cancelled immediately when the CAN reached ground. After this disturbance, the data is consistent with open air measurements. From the pressure data, we derive the altitude relative to the launch site. As you can see, the rocket reached an apex of around 329 meters before falling. After ejection, our descent velocity was stable but out of range, 20 meters per second, due to our parachute issue. More on that later.
During the flight, we wanted to see how the parachute shape, which we could change using a servo, influenced the descent velocity. We unfortunately couldn't collect meaningful data for several reasons. First, the CAN was ejected very late during the rocket descent and much closer to the ground than expected. Second, a knot that fastened the parachute to the CAN went loose and the seam located between the severed ropes didn't hold. Although this is not an excuse, we should note that the ejection happened at a velocity of around 360 km per hour. Nonetheless, the CAN piloted the experiment exactly as expected in those circumstances. The controller runs the experiment when the CAN is falling within safety limits, which is when fall velocity is between 5 and 16 meters per second and the altitude is above 115 meters. These conditions were only met twice during this short flight. In those 2 cases, the servo positioned exactly as expected, as shown. During the rest of the flight, safety conditions were not met and the servo fully deployed the parachute.
In conclusion, our architecture and design proved to be adequate. The CAN structure was undamaged, and the electronics still worked perfectly after the flight. As for the parachute, we obviously did something wrong in the final assembly, because one nut failed. Although we performed the required tests and the constraints were lower than in our tests, it still failed. We've also been able to involve many people in our project and would be happy to detail our outreach outside this strict 5 minutes time frame.